So this final video for lecture 5 refers specifically to support reactions in 3 dimensions and how they may enable support forces, or moments to exist in certain planes and certain axes, but how they'll also restrict movement in other planes or axes. So again, there are some common joints and supports like we had for the 2-dimensional questions. They can be found on slide 37 in the lecture. The 4 common ones that we've got there, we've got a smooth surface support, a ball and socket, a single journal bearing and a single hinge, but I'll briefly talk you through those individually. So a smooth support, fairly simply, it's like a leg of a chair, a leg of a it looks a bit like a leg of an easel or something in its curvature there, but basically all it's doing is providing a force stopping it falling through the floor. And you know that if you take an easel with that curved base to its leg and you push on it, it's gonna fall over. It's not doing much, so it can't take a lot of force apart from stopping it sinking through the floor. We've also got in that diagram a ball and socket. So that's a bit like your shoulder or your hip. And obviously you can get artificial ones of those. So the ball and socket joint is fairly flexible, and it can allow movement, fairly good movement. It can allow you to turn in any direction, but the forces that it'll apply, the support forces, it can go in the Y, or in the X, or in the Z. So it can support in all 3 directions. If I push on it, it'll push back. There are no support moments. There are no... if I try and turn it, it won't resist that turn. So there are no support reactions in terms of moments. So a support moment, I'll show you an example in the single journal bearing. So your diagram from the notes will be much better than mine, I'm sure. So it looks a little bit like a tube going through a holder. That doesn't describe it at all. But you've got, if you imagine the smaller piece is a rod, and it's going through a sleeve, and the sleeve, not that you can tell it there, the sleeve is fixed down. And what we can do is, if you imagine you could hold the pipe, and you could hold it where these 2 red arrows are. Okay, so you're holding it where those 2 arrows are, and I'm just going to take those out for a minute. So you're holding it in those 2 places. If you were to push on it, and you were to push on it in that direction, then it would push back. So there is, in the X direction, a support reaction. If you were to push on it downwards, then it would push back upwards. So in the Z direction, there is a support force. There's a reaction force. If I was to push on it, and I was to just push on the end of the pipe, so I was to push it that way, i.e. pass it from one hand to the other, move it through the sleeve, through the bearing, then there's no force to stop it, so there's no Y component of the reaction force. Similarly, if I held it where I talked about originally on the 2 ends of the diagram, if I was to try and turn it, in that sort of motion, so imagine it's like a pair of handlebars on the bike, and you're trying to turn left or right. You couldn't turn it because there's something stopping it. It can't turn through the bearing in that way. So there is a support moment around the Z-axis. Similarly, if I was to imagine it again, it's like handlebars on the bike, but I was to try and pull the right hand handlebar down and the left hand, push the left one upwards, or vice versa. Don't know why you'd do that, but imagine you're trying to twist them that way. So you're trying to go like that and like that. Well, you couldn't do that. You can see from the picture it's not going to move. So there is a resistive moment that's stopping it twist about the x-axis. There's a support moment about the x-axis. However, if I was to take hold of my handlebars, and you imagine the this tube here. If you imagine that rod, that tube, that pipe, whatever, is free to roll inside the bearing. If I was to try and turn it about the y-axis is going that way. If I was to try and turn it, so just spin it in my hands, a bit like revving a motorbike, you're turning it in that sort of motion. There's nothing to stop it from the bearing. So there's no resistive moment about the y-axis. There's no reaction moment. Hopefully that makes a little bit of sense. It's quite difficult to describe without some hand gestures. The final one to consider is the single hinge that's shown in the diagram on slide 37. Sorry. That was badly drawn, wasn't it? Let's try that again. There we go. So, if you imagine this is two sides of a hinge, because it is two sides of a hinge, if I was to pull on either side, then it wouldn't move. So it's like pulling, if I was to, it was a hinge on a box, if I was to pull on the box, I was to pull on the lid, neither bit would come apart from the other. So there is a support force, a reaction force, that's stopping it moving. So there's a force in the Z that stops the lid coming off, or the box coming off, and there's a force in the other direction, the X direction. Equally, if I was to get hold of my lid of my box, and I was to pull it one way, and I was to pull the box the other, it doesn't come apart. There's another force in the Y direction that stops it coming apart as well. There's a force stopping it moving. If I was to take hold of my lid of my box, we'll assume that this side here is the lid side. If I was to take hold of that with both hands and I was to try and twist it, it's not going to twist. You can't spin the lid of a box. So there is a resistive moment about the Z axis. Equally, if I was to try and twist the box, you can't twist the box easily. So there's a resistive moment about the X axis. There's no resistive moment this way, there's no resistive moment about the y-axis, because if there was something to stop it turning that way, the hinge wouldn't work. The hinge is designed to twist about the y-axis, so that last moment doesn't exist. There's no resistive moment in that axis. So that explains some of the support reactions that occur for the common support mechanisms. So you've got a smooth surface, a ball and socket, single journal bearing, and a single hinge. What you can then do is you can start to put them together, so you've got multiple supports in one system. When you put multiple journal bearings or hinges or multiple supports into one system, then you're only going to get force reactions because the moments start to cancel each other out. And often the force reactions will cancel out with other forces that exist in the system to hold it in equilibrium. And as we talked about before, in the previous video, for a system, a 3D system, to be in equilibrium, the sum of the moments about the x-axis has to equal 0, as to the moments about the y-axis, as to the moments about the z-axis. But equally, the sum of the forces in the x direction and the y direction and the z direction all have to equal 0. So you've now got 6 equations which you can potentially formulate and then solve either relatively straightforwardly, or sometimes you have to solve them simultaneously. If you have too many support reactions, too many things constraining movement, more than are necessary, then you can have the system can be statically indeterminate. So you've got more unknowns, more unknown forces or moments than you have equations of equilibrium to solve. In practice, they're not particularly practical because you can't A, you can't analyse what's happening, and B, you're using more constraints than are necessary. You can also have improper constraints. So on slide 41, you can see a case of improper constraints. There are 6 unknowns, and obviously you've got 6 equations of equilibrium. You should be able to solve that, but there's nothing to stop rotation of that pipe about the AB axis in that case. So if you haven't got the slides in front of you, there's a diagram like that, and you've got A and you've got B. And they're both ball and socket joints, and you've got a force pushing down here. There's nothing to stop it spinning about the AB axis about here. Well, that's an axis, so I should have dotted that probably. But there's nothing to stop the spinning, so it's improperly constrained. If it's not properly constrained, it can become unstable. So we have to think about that and make sure that we have not just the right number of constraints, but the right type of constraints. The questions you'll get won't necessarily ask you to put constraints in place, but they may ask you to find particular unknown support reactions with the constraints that are given. So I'll do 2 examples of that, and then I believe there's at least one for you to have a go at. So this is example 1 from lecture 5 with the 3D supports. So it begins on slide 42. And we're looking for the reactions at the thrust bearing A, so it's a single journal, it's a bearing, but also at the cable BC. And I didn't label B, apologies. BC. This diagram is much clearer when you look at it on slide 42 than the way I've drawn it. But first of all, let's think about what reactions are happening in our diagram. Well, single journal bearing. We know from our previous example that I can't push it in the x direction, so there's going to be a reactive force that way. I didn't label x, y, z. So there's resistive force that way, which we'll call AX. There's a resistive force about that axis, which we'll call MAX. We're calling it MAX for good reason, which will become obvious later. There's a resistive force this way, which we'll call AZ, and there's also a resistive force about this axis, which will become MAZ. So there are 4 resistive components. Sorry, I called it resistive force, it's resistive moment. But there are 4 resistive elements. We can then start to apply our equations of equilibrium. So our sum of our forces in the x-axis equals AX. There are no other forces acting in the x-axis, so that equals 0. In the z-axis, we've also got a tension force here, a force here from the cable FBC. In our z-axis, we've then got sum of the forces in the z-axis is going to equal AZ. It's going to equal FBC. That's going to add on because they're both positive direction. And we've got minus 80 acting downwards, so we can't solve that on its own yet. Our sum of our moments, if we take some of the moments about the y-axis, we'll only have one unknown. So some of the moments about the y-axis, well, we're going to have, that's all the forces and all the moments that are trying to turn it about this axis here. So we've got 80 kilonewtons that's trying to push down 1.5 metres from the y-axis. So it's going to be negative because it's trying to turn it clockwise. It's 1.5 metres away. And we've also got FBC trying to pull up, so it's positive, and it's 3 metres away. They're the only 2 forces and moments acting about the y-axis. So we can rearrange that and we can solve FBC. And that will equal 40 kilonewtons. And we can then substitute that into the sum of the forces in the z direction, and AZ will also equal 40 kilonewtons. So we've now found some of our forces and moments. We now need to find the rest. So if I jump to the next page, my moments about the x-axis are going to equal my moment at A about the x-axis, which is the one we said was a reaction from the bearing at A. I've also got 40 kilonewtons, i.e. FBC. FBC is acting 6 metres from the x-axis, so I'm going to have plus 40 times 6. It's trying to turn it anti-clockwise, because if you look, it's pulling it upwards, and it's 6 metres away, it's pulling it upwards, it's going to try and turn anti-clockwise about the x-axis. I've also got 80 kilonewtons acting also 6 metres away, but in the opposite direction. So I can rearrange that to find MAX, a moment at A about the x-axis, 240 kilonewton meters, and that's going to be going anti-clockwise, which is the direction we originally assumed. And finally, my moments about Z, these should have sums on them, are going to simply equal MAZ. There's no other moment about Z. That has to equal 0, so we know the moments about at A about Z equals 0. That's the conclusion of example 1. I'll now talk you through example 2, and then there's one for you to have a go at. So this is example 2, where you've got a uniform plate with a weight of 500 kilonewtons. So the first thing we can do is we can label the weight on that. That's going to be acting in the centre of the plate. And we know it's got a magnitude of 500, so we know it's acting 1.5 metres along here, and we know it's acting 2 metres in, so in a line with the 200 Newton force, on the same line there. We've also got 3 tension forces. We've got a tension at A, a tension at B, I have to draw it a little way in because I've gone right close to the edge, and a tension at C. So that's our free body diagram for our plate. We can now start to do our equations of equilibrium. Well, in this case we've got no x or y equations, we've only got the z direction where z is upwards, the same direction as the tensions. So the sum of our forces in the z direction is going to equal our tension at A plus our tension at B, that should be T at B, plus our tension at C, and then it's going to be minus 200 and minus 500. That has to equal 0. We can also say our sum of our moments about the x-axis and our sum of our moments about the y-axis. Well, about the x-axis, if we're calling this the x-axis, which it does in the question, we've got our tension at A is going to be trying to turn it anti-clockwise, so it's going to try and turn it that way. Sorry. And it's acting 3 metres away. We've got our tension at C, which is doing the same thing and acting 3 metres away. We've got 500 kilonewtons and it's acting the opposite way, so it's minus 500 and it's acting 1.5 metres away. And we've got minus 200 that's acting 3 metres away. We ignore the TB because it's acting 0 metres away. But all of those add together to equal 0. And we've also got our sum of our moments about the y-axis, and the same principle occurs. The y-axis is this axis here, so we can ignore TA this time because it's 0 metres away. TB is trying, and TC are both trying to turn it clockwise, so minus TB, and they're both 4 metres away. And the 500 and the 200 are both 2 metres away and are both trying to turn it in the anti-clockwise direction about the y-axis. So now we've got 3 simultaneous equations and we can solve those and we can find our TA, our TB, our TC. So taking those, the first thing we do is we can use equations 2 and 3, so some of the moments in x and some of the moments in y, and we can get TA and TB in terms of TC. So, for instance, we're going to have, rearranging the sum of the moments in x, we're going to have TA equals 450 minus TC. And rearranging the sum of the moments in y, we're going to have TB equals 350 minus TC. And we can then substitute those into one of our equations. So the lecture notes have substituted them into equation 1. So we're going to get 450 minus TC instead of TA, plus 350 minus TC instead of TB, plus TC, the original TC, minus 200 minus 500 equals 0. So TC comes out at equaling 100 kilonewtons. Once we've done that, we can then substitute TC back into the sum of the moments in X and the sum of the moments in Y. And we can get TA rearranged to find TA to equal 350 kilonewtons and TB to equal 250 kilonewtons. And if you are following this in the lecture notes, slide 47, there is a typo. The second answer where it says TA equals 250, that should say TB equals 250 kilonewtons. So that concludes the two examples that I'm going to do with you initially. There is one exercise, group problem exercise, beginning on slide 50 of the lecture notes, for you to have a go at. And when you've had a go, if you come back to this, I'll then talk you through how to solve it. One thing you should notice is that solving simultaneous equations is crucial when you're looking at these problems. So you should have had a go at the group problem solving exercise beginning on slide 50. This is the free body diagram, or it's the beginning of the free body diagram for what you should have started labelling there. So there's several different reactions we can add on to this. A, in the X direction, if I was to push A in the X direction, so if I was to push that way, it's just a shaft on a pipe, so it would just slide. There's no reaction force to stop it, so there's no forces in the X direction. If I was to try and pick up, if you imagine holding the bar at where the 800 Newton force is acting, I could pick it up and I could spin it about A, so there's nothing to stop it spinning in the around the X-axis. Similarly, if I was holding it in the same position, I couldn't twist it around the Z-axis. I couldn't twist it about the Y-axis, so I can't twist it that way. So there must be a moment at A about the Z-axis. And I can't twist it that way, so there must be, and I'm going to label this just here, a moment at A about the Y-axis. Similarly, I can't pull along the Y-axis. I can't get hold of the pipe at B and just pull it along the Y-axis. So there must be a resistive force here, Fay, and I can't just pick it up and it come off the plane. So there must be a force Faz. And the final force is not sinking through the support reaction at B. It's not falling through the floor. So there must be a normal force, a reaction force at B. Now we've spotted all those support reactions, it's a case of forming my equations. So we'll start with the ones where there's fewer unknowns. The sum of the forces in the Y is just going to equal AY. There is only that AY force, Fay. Help if I label it the same way I'd label it in the question, in my notes. Fay. That's just going to equal 0. Now, the next one we could look at is the sum of the moments about the Z-axis. Well, sum of the moments about the Z-axis, there's nothing pushing in the X or the Y-axis. So there's no moments about the Z-axis apart from the one we've identified, MAZ. So that also equals 0. We can do sum of the moments about the X-axis. Some of the moments about the X-axis, we've got our normal force at B. And that's acting 1.6 metres perpendicularly from the X-axis. And that's going to try and turn it anti-clockwise, so it's positive. We've also got the 800 newtons acting 0.8 metres from the X-axis, trying to turn it clockwise, so it's negative. And similarly the 600 newtons turning it the same direction and again acting 1.6 metres away. They all equal 0, so we can solve NB to be 1000 newtons. Some of the forces in the Z direction, we've then got our AZ, which I haven't called AZ, I've called FAZ, force AZ. We've got 1000 newtons at B. We've got 800 acting downwards and 600 acting downwards that we started with, equaling 0. So FAZ has to equal 400 newtons. And the final one, I'm just going to have to skip to the next page. Some of my moments about the y-axis is going to equal a moment A about the y-axis. I'm going to have 600 newtons acting downwards, 0.4 metres from the y-axis, because my y-axis is just here. So 600 newtons is acting 0.4 metres away, and it's going to try and turn it clockwise, so it's negative. I've got 1000 newtons that's acting upwards, so going the opposite way, so it's positive, and it's acting 0.8 metres away. And they're the only things that are trying to turn it about the y-axis. So I can say my moment at A about the y-axis is equal to minus 560 newton meters, or the opposite direction to the one that we originally assumed. In fact, I've assumed a different direction to the lecture notes, so I've assumed the opposite way, so it will come out positive already. So that concludes the three-dimensional group problem-solving activities on equilibrium of rigid body. It looks at all the support force reactions that you may encounter to do with equilibrium of a rigid body, and concludes lecture 5 of the statics lecture series. If you've got any questions on anything you've encountered, please feel free to email me. There are a series of tutorial questions you should now be able to solve based on those lectures and these videos.